called AVL trees. I've been calling them AVL trees since I was your age. And who are they? Well, A, V, and L are some, or I guess there are only two guys. This guy must be AV and this guy must be L. But, you know, they're dead white guys. But one thing that's true about many things in computer science is if you ask mathematics, when did it happen, right? You might have to go all the way back to Euclid. But if you ask computer science, when did it happen? It all happened post the 60s, right? They didn't have computers before the 60s. So these guys, they got in and they did all the low-hanging fruit, right? Anything they wanted to do, they solved all these problems quick, right? All right. So what is an AVL tree, right? It's not going to be, this actually is an AVL tree, I assume, and it doesn't look completely balanced, right? But it's what we call, it's enough balanced, right? And what's our definition of enough? Is you calculate the height of every node, all right? So let's see if we, here, right, this node here has height 2, say, right? Because there's this node and this node is height 2. And this subtree has height 3, right? Everybody see that? And so what's true is the difference between their heights is 3 minus 2, right? You calculate the height of the left and the height of the right, and there's a typo in here. Height. Yeah, this doesn't look right to me. It should be the height of the left minus the height of the right. All right. So who made this slide? This one clearly wasn't done by me. That was a joke. All right. So here, 2 minus 3 is minus 1, right? So minus the difference, the balance factor has to be minus 1, 0, or positive 1, right? And you need that to be true for every node, right? So look at node 17. The height of its left is 0. The height of its right is 1. So the difference is minus 1 or 1, right? Right? Everybody follow that? Well, so this guy is, right, we label in fact, we're going to store that extra information is that we're going to label the difference, right? If I come down to 44, the minus 1 tells me that the left side is 1 shorter than the right side, right? Well, this guy here, the left is 1 deeper, right? That's why it's plus 1. And this node here has a balance of 0, right? Because it's 1 minus 1. Right? Everybody get the green labels? Right? All right. So a tree is an AVL tree if for every node this balance factor is -1, 1, or 0. Right? So it gives you some balance requirements. Right? Everybody buy that? All right. Now we're going to prove a theorem. And let me tell you right now, proofs are good and you should be able to enjoy them. And I can't imagine me putting the proof on the test. But you know, it's good to know the proof. All right, so here we have 2 things about a tree, right? We have its height and we have its number of nodes. So in the first line is, I tell you how many nodes you have, and I want the tree that's an AVL tree and that is deep as absolutely possible and still be an AVL tree within nodes. And the claim is it can't be deeper than order log n, right? And it might not be order base 2 log n. Maybe there's an extra times 2 or times 3 here, right? Now, if you take kind of the dual of that, it's not, you flip it around. Now, I'm saying I'm looking at all trees of height h, and I want them to have as few nodes as possible, right? You can see it's kind of the flip of this. Here we want as deep as possible. Here for a fixed number of nodes. Here we want a fixed height. We want as few nodes as possible, right? So the relationship between these is the same, right? Does that make sense? All right. So, right, n of h tells me how many nodes I can have of height h. And n of 0, I got 0 nodes, height 0. N of 1, I got 1 node, the height is 1, right? Now, we're going to do some, oh, look at that. Do you know what that is? That's the output from one of my first-year programs. Oh, no, it's the output from you guys rotating. All right? All right, so here, this here is, we want to find the tree of height h that has as few nodes as possible, right? So let's say that our height's 5. What are we going to do on the left side? Well, we need something of height 5, right? So on this side, we're going to put a tree of height 4 so that this can be a tree of height 5. But we want as few nodes as possible, right? So, and it has to be an AVL tree, right? And then what do we put over here? Well, it doesn't have to be a height of 4. It can be, there can be a shift, right? It's smaller. So it can be of height 3. Does that make sense? This one's going to be height 4. This one's going to be height 3, and they're both the AVL trees, right? So here, that one's height 4. That one's height 3. And what do we get here? We get that the number of nodes you need here is the number over on the left plus the number over on the right for an AVL tree of that, right? Plus the root, right? Does that make sense? Right? Because this is an AVL tree of height 4, which is few as nodes as possible, right? So that's n of h minus 4. It's the number of nodes you need in a height of 4. And this is the number of nodes you need in a height 3. So we got the number of nodes, minimal number of nodes here, plus the root, right? Does that make sense? And so you get this recurrence relation. Does this remind anybody of anything? What does it look like? Fibonacci's, right? It's the one messes us up by Fibonacci's, but it's close enough, right? If you ignore Fibonacci, oh, and we want to show that, besides, we want to show that n is big, right? So we can ignore the 1 and it only helps us, and we get Fibonacci's. And you might, did you guys ever learn that Fibonacci has this value, more or less? Right? Anyway, it does. And so then that gives us that n's bigger than this, which gives us that h, the height is the most 4.78 times the log. Yeah? So I'm saying, give me an AVL tree that has h, that has height h, and as few as nodes as possible. Well, because, right, so here, let me write it on the board here. We want, we know in our real problem, we have n nodes, and we want the worst case, right? The worst case is when h is big as possible, right? We want the AVL tree that has the biggest height given you have n nodes, right? And n is fixed. right? So let's change it slightly. Let's make this fixed and make this a marker that doesn't work, right? Make this as small as possible, right? So can you see it's sort of solving the same problem, right? Because if you make this smaller, then this gets smaller, right? It's sort of saying that the worst case is it's not that big, right? And so it's solving the same problem, right? I mean, here you can see it right in this relationship here. It says the smallest n has to be at least this, right? So the other way of saying it is the biggest h has to be bigger than this, right? So the biggest h is still smaller than that, right? We turned it around, right? Does that make sense? So that gives us the height of an AVL tree is log n, right? Everybody good?